time, distance and shielding. There are three general guidelines for controlling exposure to ionizing radiation. Minimizing exposure time. Maximizing distance from the radiation source. Shielding yourself from the radiation source. Time is an important factor in limiting exposure to the public and to radiological emergency responders. The amount of radiation exposure increases and decreases with the time people spend near the source of radiation. The maximum time to be spent in the radiation environment is defined as the stay time. The stay time can be calculated using the following equation. Stay time equals exposure limit, dose rate. Distance can be used to reduce exposure. The farther away people are from a radiation source, the less their exposure. Doubling the distance from a point source of radiation decreases the exposure rate to 1/4 the original exposure rate. Halving the distance increases the exposure by a factor of 4. How close to a source of radiation can you be without getting a high exposure? It depends on the energy of the radiation and the size, or activity, of the source. Distance is a prime concern when dealing with gamma rays, because they can travel at the speed of light. Alpha particles can only travel a few inches and beta particles around 10 feet. Shielding. As ionizing radiation passes throughout matter, the intensity of the radiation is diminished. Shielding is the placement of an absorber between you and the radiation source. An absorber is a material that reduces radiation from the radiation source to you. Alpha, beta, or gamma radiation can all be stopped by different thicknesses of absorbers. Shielding material can include barrels, boards, vehicles, buildings, gravel, water, lead or whatever else is immediately available. Stop alpha 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 can be stopped after traveling through about 1.2 inches of air, about 0.008 inches of water, or a piece of paper or skin. A thin piece of paper, or even the dead cells in the outer layer of human skin provides adequate shielding because alpha particles can't penetrate it. However, living tissue inside the body offers no protection against inhaled or ingested alpha emitters. Beta stop beta beta can only be stopped after traveling through about 10 feet of air, less than 2 inches of water, or a thin layer of glass or metal. Additional covering, for example heavy clothing, is necessary to protect against beta emitters. Some beta particles can penetrate and burn the skin. Gamma to reduce typical gamma rays by a factor of 1 billion, thicknesses of stop gamma shield need to be about 13.8 feet of water, about 6.6 feet of concrete, or about 1.3 feet of lead. Thick, dense shielding is necessary to protect against gamma rays. The higher the energy of the gamma ray, the thicker the shield must be. X-rays pose a similar challenge. This is why X-ray technicians often give patients receiving medical or dental X-rays a lead apron to cover other parts of their body. Radiation. What is radiation? Radiation is energy that travels as particles or waves and can be naturally occurring or man-made. It is all around us in various forms ranging from radio waves to X-rays to cosmic radiation. We gain benefits from this energy and we classify these energies into two main types. Non-ionizing radiation has enough energy to excite atoms, making them move more rapidly. Examples of non-ionizing sources include microwave ovens, radio transmissions, cell phones, and visible light. Ionizing radiation has enough energy to change atoms by remove electrons from them, a process called ionization. Examples of ionizing sources are X-rays, nuclear power plants, and smoke detectors. There are three main kinds of ionizing radiation. Alpha particles, which include 2 protons and 2 neutrons. Beta particles, which are essentially high-speed electrons. gamma rays and X-rays, which are pure energy, photons. Radiation detection. You cannot see, hear, smell, taste, or touch radiation. You can only detect radiation with special equipment. Detecting non-ionizing radiation, NIR. Since non-ionizing radiation is simply low-energy waves of the electromagnetic spectrum, radio waves or microwaves, detection is hard. The easiest way is to look for any nearby antennas, satellite dishes, or radio towers. Or, if you can listen to your radio, watch TV, have cell service or use wireless internet, Bluetooth, wireless mouse or keyboard, you are definitely being exposed to NIR. To measure the quantity of radio, microwaves, you will need an EMF, electromagnetic field, meter. A very simple way to determine the wavelength of NIR is the length of the antenna. As a general rule, the shorter the antenna, the more energized the waves. To pick up radio waves, an antenna must be the length of the longest wavelength. You can compare the antenna length to the electromagnetic spectrum chart to find the energy intensity. Detecting ionizing radiation. Geiger counter-ionizing radiation can be measured very precisely, much more precisely than other potentially hazardous materials. One of the basic measuring instruments is the Geiger-Müller counter. The instrument consists of a detector set at the end of a probe with counting electronics. This instrument counts the number of radioactive particles entering a sensitive detection chamber, and translates that signal into a needle movement on an analog dial or a value displayed on a screen. The Geiger counter emits a click for every particle, so with only background radiation, the instrument clicks every few seconds. In a high radiation environment, it clicks rapidly in proportion to the radiation level. This way, the user gets a visible as well as audible measurement of radioactivity. Some people receive exposure to radiation as part of their employment, radiologists and nuclear plant workers. Worker radiation exposures are carefully monitored to ensure that everyone's exposures are kept as low as reasonably achievable. ALARA. Individual film badges and personal dosimeters are useful for this purpose. In the film badges, the amount of film darkening is a measure of the radiation received, so by analyzing the film, radiation exposure records for each individual worker can be kept. Personal dosimeters allow the workers to view their own radiation dose instantly by looking at a small scale magnified by the instrument. Biological effects. We live in a radioactive environment. We are subject to background radiation all the time, and the normal levels are well known. Radiation is in the air we breathe, the food we eat, and the places in which we live and work. There is evidence to suggest that unless radiation exposure reaches 10 times the normal background level, there is no harm to humans from radiation. Furthermore, there appears to be evidence that radiation at or near the normal background level may be beneficial to, and even necessary for life. For low levels of radiation exposure, under 10,000 mrem, the biological effects are so small they may not be detected. The body's natural repair mechanisms often repair any damage to the cells before any effect is felt or detected. This protective effect of low levels of radiation is called radiation hormesis. Too much radiation, like too much of anything, is harmful. The effect of too much radiation, over 50,000 mrem, can range from mild gastrointestinal problems, such as nausea and vomiting, to changes in the blood, to damage to the central nervous system. High levels of radiation dose have caused cancers, leukemia, breast, ovarian, pancreatic etc., and led to death. Most people who died at Hiroshima did not die from the radiation, most died from the blast of the bomb and subsequent fires. Studies have shown that cellular cultures, protozoa, could not grow normally when they were deprived of background radiation. Lucky TD. Between 1978 and 1987, 108,000 nuclear submarine workers were compared to 700,000 other shipyard workers. There were 24% fewer cancers among those exposed to low doses of radiation. The Colorado Plateau, with higher background radiation levels, has 15% fewer cancers than the national average. Isotopes. Ions are atoms that are either missing or have extra electrons and so have a charge. Let's say an atom is missing a neutron or has an extra neutron. That type of atom is called an isotope. Radioactive isotopes or radioisotopes are isotopes of an element having an unstable nucleus that decays, emitting alpha, beta, or gamma rays, until stability is reached. The stable end product is a non-radioactive isotope of another element. Uranium, U, is a metallic, silver-gray element that is a member of the actinide series. The radioisotope uranium-238 has 3 more neutrons than uranium and decays to lead-206. Since small traces of radioactive isotopes can be detected to a high degree of precision, they have various uses in medical therapy, diagnostics, and research. Domestic sources of radioisotopes are needed to adequately sustain the growing use of this technology to ensure our productivity, security and competitiveness and to meet the growing needs of our medical and healthcare communities. Promising research, in areas such as cancer, cardiovascular disease and rheumatoid arthritis, has been delayed or abandoned because certain radioisotopes have been unavailable. Geologists, archaeologists and police rely on radioisotopes to determine the age and chemical composition of materials. Biologists explore the use of radiation in food preservation and in agriculture to develop better fertilizers, control insects and improve plant breeds. Nuclear fission. Nuclear fission is the splitting heavy nuclei, such as uranium-235 and plutonium-239, into gamma rays, free neutrons, and other subatomic particles. Fission. Imagine about 100 marbles lying on a flat surface and roughly forming a circle. What would happen if you took another marble and threw it at them? They would fly all around in different directions and groups. That is exactly what happens in nuclear fission. The filled circle is like an atom's nucleus. The marble being thrown is like a neutron bullet. Fission as encountered in the modern world is usually a deliberate man-made nuclear reaction. Nuclear fission, nuclear fusion. Definition: fission is the splitting of a large atom into 2 or more smaller ones. Fusion is the fusing of 2 or more lighter atoms into a larger one. Natural occurrence of the process. A closed natural fission reactor's fusion occurs in stars, such as the Sun. Byproducts of the reaction. Fission produces many highly radioactive particles. Few radioactive particles are produced by fusion reaction. But if a fission trigger is used, radioactive particles will result from that. Conditions: critical mass of the substance and high-speed neutrons are required. High density, high temperature environment is required. Energy requirement: takes little energy to split 2 atoms in a fission reaction. Extremely high energy is required to bring 2 or more protons close enough that nuclear forces overcome their electrostatic repulsion. Energy released. The energy released by fission is 1,000,000 times greater than that released in chemical reactions, but lower than the energy released by nuclear fusion. Fission U-235 plus N is a total of 236 SAMU, then 180 megaelectronvolts / 236 equals 0.763 megaelectronvolts per nucleon. The energy released by fusion is 3 to 4 times greater than the energy released by fission. Fusion D plus T releases 17.6 megaelectronvolts. D equals 2 atomic mass units, AMU, and T equals 3, so total is 5, then 17.6 megaelectronvolts / 5 equals 3.52 megaelectronvolts per nucleo. Nuclear fusion. Fusion is the process by which the Sun and other stars generate light and heat. It is a nuclear process, where energy is produced by smashing together light atoms. It is the opposite reaction to fission, where heavy isotopes are split apart. It's most easily achieved on Earth by combining two isotopes of hydrogen, deuterium and tritium. Hydrogen is the lightest of all the elements, being made up of a single proton and an electron. Deuterium, often called heavy water, has an extra neutron in its nucleus. Tritium has 2 extra neutrons, and is therefore 3 times as heavy as hydrogen. In a fusion cycle, tritium and deuterium are combined and result in the formation of helium, the next heaviest element in the periodic table, and the release of a free neutron. Deuterium is found 1 part per 6,500 in ordinary seawater, and is therefore globally available, eliminating the problem of unequal geographical distribution of fuel resources. This means that there will be fuel for fusion as long as there is water on the planet. Scientists from the Max Planck Institute for Plasma Physics in Greifswald, Germany, have demonstrated that it is possible to superheat hydrogen atoms to form a plasma of 80 million degrees Celsius using a machine called the Wendelstein 7X stellarator. The plasma forms the basis for nuclear fusion, in which hydrogen atoms collide and their nuclei fuse to form helium atoms, a process which lets off energy and is similar to what happens in our Sun. What is fusion power? Let us take a look at a fusion reaction. You can see that as deuterium and tritium, the 2 heavy isotopes of hydrogen, fuse together, their component parts are recombined into a helium atom and a fast neutron. As the 2 heavy isotopes are reassembled into a helium atom, you have extra mass left over, which is converted into the kinetic energy of the neutron, according to Einstein's formula, E equals mc2. Nuclear technology continues to make the world a better place, through relatively inexpensive electricity, lower greenhouse gas emissions, and radiation therapy for cancer patients. In the international community, there is continued interest in nuclear power to improve the standard of living and the power industry. It is important for all of us who support the nuclear field to be cognizant of the various issues surrounding nuclear energy and to be ambassadors to our communities and to help inform, engage, and inspire others. Nuclear science and technology improves our lives in many ways and in many different areas. It makes our food safer, it improves the quality of tools, gauges, and machines. It diagnoses abnormalities of the metabolism and treats cancers. It powers space applications, and it offers one of the cleanest and the most environmentally friendly ways of generating electricity. Energy, isotopes, and radiation produced by nuclear science provide for a vast range of beneficial applications. Nuclear science and technology faces many challenges, from public education and acceptance, to regulation and funding. Beginning a conversation about nuclear topics is not always easy. Whether from a podium or over a cup of coffee, talking about complex nuclear issues requires preparation, and an understanding that the general public may not grasp, or care about. the fine details. The resources in this section provide relevant information and simple facts that will help everyone from nuclear scientists to educators.